Hello everyone, this is Cui Kai. My English name is King. I come from the School of Public Health, Jinzhou Medical University. Since today, I will be your statistical teacher. Since today, we are going to start a new part of medical statistics. Today we are going to learn Chapter 4, Introduction to Statistical Inference. Before starting our today's class, I will show you some rules. Maybe some of you are wondering about your final marks. Here I will show you that. In our full marks for medical statistics will be 100 marks. I divided that into 4 parts. The first one is your regular score. That will be 15 marks. So that means if you are, for example, absent from our class, you will lose some point. The second part is practice class. You will have 15 marks for that. And in this 15 marks, there will be 5 marks that will be decided by if you are absent or not. And the rest 10 marks will be your practice report. In our practice class, you have to finish your practice report after the class and send it to the teacher. The third part is your homework. That will be 10 marks. I will give you some homework and you need to finish that after the class. The last part is the final exam, and the final exam will occupy 60 marks in our final result. So that is the 4 parts of your final results for medical statistics. In today's class, this is our learning goals. So the first one, to master some basic concepts. For example, the concepts of standard error of the mean, hypothesis testing, confidence intervals, the general hypothesis testing procedure. And the third one is to be familiar with the concepts of type 1 and type 2 error. The last one is to understand the p-value, sampling distribution, and central limit theorem. So that is all what we need to do in chapter 4. Okay, so here let's review what we have learned in chapter 1 to 3. In the previous chapter, we examined the properties of several important probability distributions. For example, the most important distribution is normal distribution. And we have already learned a special normal distribution, that is the standard normal distribution. We also call it Z distribution. In those cases, we have always known the values of the parameters of the distribution, but it's unlikely that we will know these values in actuality. So most commonly, we collect a set of data and we want to infer the properties of the underlying distribution from this data set. At this time, statistical inference can be used, and this method can be subdivided into the two main areas of estimation and hypothesis testing. So that means there are two methods in statistical inference. So the first one is estimation, and the second one is hypothesis testing. And estimation is concerned with predicting the values of specific population parameters. That means we want to know the parameters of a population, but we know that the population is too big. So here we can know nothing about the population. For example, we don't know the mean or the average of the population because we cannot measure the individuals in the population one by one. So we cannot know the parameters of the population. But we can draw some special individuals from the population. For example, we can choose 10 individuals from the population. So we call these 10 individuals as a sample. And here we can calculate some numbers or some errors with the data of the sample. And here we can use the results of the sample to infer the values of the population. So that is estimation. And the second method in statistical inference is hypothesis testing. Hypothesis testing is concerned with testing whether some statement about the numerical value of a population parameter is consistent with the sample results. So sometimes we want to know, for example, we have two medicines, medicine A and medicine B. We want to know which one is better, medicine A or medicine B. So we need to compare the effectiveness of these two medicines. But actually, we need to use medicine A or medicine B on all of the patients. That means every patient need to take medicine A or medicine B. But that is impossible, right? We cannot find out all the patients around the world. So how can we solve that question? How can we know which medicine is better? So we can use two samples. For example, we choose 10 patients to be group A and another 10 patients to be group B, and we let all the patients in group A use medicine A and the other group use medicine B, and then we can compare the effect of these two groups, these two samples. So here, with the data of the two samples, we can know which one is better. But don't forget that what we really want to know is the effect of the medicine for all of the patients, not just for these 10 patients or the other 10 patients. So here we can use the result of the comparison of the two samples to infer the results of the comparison of the two populations. The two populations means population A is all of the patients who take medicine A, and population B who take the medicine B. So that is what we want to do in hypothesis testing. So we can find that estimation and hypothesis testing, they are different. Estimation is to predict a special value with a special number of sample. But hypothesis testing is to compare the two populations with the data of two samples. So that is the difference between these two methods. Okay, so here let's learn some basic definitions and concepts. The first one is sampling. So the first problem faced by a research is that of collecting data. We just mentioned that the population is so big, so large, so we cannot collect all the data of all the individuals in the population. So once the population and the variables of interest have been defined, applicable sampling procedures will be used to obtain a sample that truly represents the population from which it's drawn. So sampling is used extensively today for many reasons. In many situations, a sample produces more accurate information about the population than that provided by a census. So, what's the meaning of census? So, census means that is the procedure of the systematically acquiring and recording information about the members of a given population. So that is the definition I found from Wikipedia. So from this definition we can find that census means we need to check or to mirror all the individuals one by one. So that means if the population there are 1 billion individuals in the population, we need to check, we need to mirror all of these 1 million individuals one by one. So that is very difficult, right? But sometimes census are necessary. For example, a national population and housing censuses. We need to know how many persons in this country. So we need to check all the individuals one by one. So at this moment we need to do the census. But we can know that the census must be incomplete because it's commonly that we will miss some information. You cannot find everyone in the census. You must lose some person. You must miss someone. So it's impractical. It will cost too much money and too much time, and also will miss some informations. So most oftenly, we use another method to do the research. That is sampling. So sampling means this method is used to obtain a sample that truly represents the population from which it's drawn. Most oftenly, when we want to know something about a population, and we also know that the population is too big to do the research, so we can draw someone from the population. So this procedure is called it as sampling. So that means we choose some persons, or we choose a group of individuals from the population. So that means the number of the patients of the sample must be less than the population. We can choose 10 from the 1 billion people. So compared to the census, sampling will be faster and cheaper. So sampling is used extensively today for many reasons. For example, it's faster and cheaper. So here we have a picture to explain the meaning of sampling. So this part means a population. So we can find that the population is so big, and the value to represent this population is called it as parameter. So most oftenly, the parameter of the population is unknown because the population is unknown. And here we can use the method of sampling to do the research with the population. So we can draw some individuals from the population. So this procedure is sampling. And we get a small part, a small group of people. So this group is called it as sample. So we can find that all the individuals of the sample comes from the population. So how can we choose the sample? How can we draw the individuals from the population? So can we draw, for example, we draw all the women from the population. Is that right? Of course not. Because we want to use the sample to infer the population. So that means the sample must be close to the population. In this population, there will be men and women. So we cannot just choose women to be the sample. So how can we solve that question? How can we solve that problem? We can draw randomly from the population. So that is an easy and very useful way to draw the sample. We use the data of the sample to calculate some special number, some special value. This kind of values are calculated with the data of the sample, so we call it statistics. Statistics can represent the property of this sample, but not the population. So we need some special methods to infer the property of the population with the statistics. So this procedure is statistical inference. So here we can know that what we really want to know is the parameter of the population. Or we can say that what we really want to know is the property of the population. But we cannot do that because the population is too big and we can know nothing about the population. So we choose another way. We draw some individuals to be the sample. And the next one, we study this sample and we can calculate the statistics with the data of the sample. And then we use the value of statistics to infer the population. By this way, we can know the property of the population. So this is statistical inference. Okay. After the concept of sampling, next one is sampling distribution. We will find that the sample, the values of the sample, will follow a special distribution. So that's very interesting. So here, this is the part of sampling distribution. In order to make inferences about a population, it's necessary to discuss sample results further. So when a mean x bar is obtained from a sample, we do not expect it be exactly equal to mu, the population mean. So here, similar with what we mentioned before, this is the population. This is a sample which is randomly drawn from the population. And with the data of the sample, we can figure out some special values. For example, x bar. We have already know what's the meaning of x bar. That is the mean, right? Actually, x bar is mean of the sample, not mean of the population, right? The mean of the population is mu. Mu means the mean, the average of the population. So we say that mu is a parameter. It's one of parameters of the population, but x bar is only is just one statistic of the sample. So that's the thing about it. If x bar is exactly equal to mu, is that right? Let's think about the procedure, the whole procedure. This is an unknown population. We know nothing about the population. We don't know the parameter. We don't know the mu. And here we use the method of sampling. We get a sample from the population. And then we calculate x bar with the data of the sample. So does that mean x bar is exactly equal to mu? Of course not. Right? Because we know that sample is smaller than the population. There will be 1 million persons in the population, but there may be only 10 persons in this sample. So a statistic is not exactly equal to a population parameter. But we expect X bar to give us an indication of the true value of mu, a ballpark figure, if you will. But how close will X bar be to mu? Of course, the answer to that question depends on several things. It will depend on the sample size, namely the little n, since we would expect a truer representation of the population from a sample of 100 observations than we would 1 of 10. It should also be obvious that 5 different random samples give 5 different values of X bar. In fact, we can construct a whole distribution of X bars called the sampling distribution of the sample means. So, the sampling distribution of any sample statistic from random samples of size n is the distribution of the statistic overall random samples of size n from an underlying or parent population. So here, let's think about this question. From the same population, if we draw 5 different random samples from this population, we can get 5 samples, right? With the same sample size. But we can still figure out a X bar with the data of each sample, and then we can get 5 X bars. So are all the X bars the same? Of course not, right? Well, no. The 5 X bars must be different. Sometimes they will be the same, but most often they will be different. Why? Okay, that's because when we randomly draw samples from the population, we will choose different individuals, right? Okay, so here we know that from the same population, we draw 5 different samples and we can get 5 different X bars. And the next question, which one of the 5 X bars is closer to mu? If we want to answer the question, we need to know the distribution of X bars. So the distribution of X bars, or we can say that the distribution of statistics, that is the sampling distribution. So if we repeatedly draw samples with the same sample size from a population, then we can construct a whole distribution of X bar. So that means we can get so many samples and we can figure out so many X bars. We have so many numbers of X bar, and we take X bar, all the numbers of X bars, as a new data, and we can use what we have learned in chapter 2 to know the distribution of this new data. So maybe it follows a normal distribution or a skew distribution. So this is the sampling distribution.
especially when we are talking about the X bar, is called the sampling distribution of the sample means. Actually, that is the distribution of X bar. So please notice that in chapter 4 we are talking about the distribution of the means, the sample means, not the distribution of the original data. In chapter 2, when we learned the normal distribution, actually it means the distribution of the original data of X. The original data, we use X to represent the original data. So that is the distribution of X, not X bar. So what's the meaning of X bar? X bar is a small group of data which is randomly drawn from all the data of X. So X bar is the mean of that small group numbers. So here in chapter 4 we are talking about the distribution of X bar of the sample mean. It's not the distribution of the original data, so they are different. You need to notice that. Okay, so here let's see this picture, and I try to explain this procedure for you. Here, this is a population, a given population. Assume we know something about the population, and here we draw samples from the population. So the first time we draw sample 1 from the population, and the sample size of this sample, for example, is 20 individuals. We choose 20 individuals from the population, and these 20 individuals is sample 1. This group is sample 1. And with the data of sample 1, we can figure out the mean, the sample mean. And we use X bar 1 to represent the sample mean of sample 1. Okay, so this is the first time. And the second time, we still draw samples from the same population with the same sample size. We still choose 20 individuals in the population, and this time we can get sample 2. We can get sample 2, and here we will find that maybe these 20 individuals are totally different from sample 1, right? Okay, so here when we get sample 2, we can get X bar 2. It's similar with X bar 1. X bar 2 is the sample mean of the second sample, sample 2. Okay, so here next one, we can repeat this procedure and we can get sample 3 and X bar 3, and we repeat it again and again, and we can get X bar 4, X bar 5, and so on. If we want to do, we can get so many X bars, right? So here we can find that all of these numbers are sample means, right? Each number is a mean of a sample. So here, let's just forget the sample mean. We just take this one as a number. This is the second number, and we can consider all of these numbers as a new data. Right? We can take it as a new data. And we can use the method what we have learned before chapter 4. We can know the distribution of this new data. So what can we do? What method can we use if we want to know the distribution of this new data? Do you remember that? In chapter 2, we have already know how to construct the frequency table, right? And the histogram. And with the frequency table and histogram, we can know the distribution of a group of data. We can know if the data follows a normal distribution or not, right? Okay, so here we use the same method. We can know the distribution of X bars. Okay, so here let's take another example. This example is better than the later one. So here let's think about it. This time we use 4 numbers to be the population. So the 4 numbers are 0, 1, 2 and 3. So these 4 numbers are the population. And then we randomly draw 2 numbers from the population. So that means the sample size is 2 because each time we choose 2 numbers from the population. So here it means the probability of selecting any one number is 1 over 4, right? Okay, so here when one number is drawn, and then the number must be returned to the population before the second number is drawn. And let's go back to this picture. Here, this population is consisted with 4 numbers, 0, 1, 2, and 3. And we also draw samples from the population with the same sample size. And we just mentioned that each time we draw 2 numbers from the population. So that means the sample size should be 2. Okay, so here let's think about it. How many combinations can we get? Or I can say that how many samples can we get? The first time we choose 2 numbers, maybe we can get 0 and 0, right? And next time we can get 0 and 1. And maybe we can get 0 and 2, 0 and 3, right? Okay, so here for each sample we can figure out the mean. When we get 00, the mean should be 0 plus 0 divided by 2, right? So the mean is 0. If we get 0 and 1, the mean, or we can say X bar, should be 0.5. If we get 0 and 2, X bar is 1, right? So here, let's list all the combinations in this table. So we can find that we can get 16 possible samples, right? We choose 2 numbers from 4 numbers, and we can get 16 combinations. That means 16 possible samples. And we'll figure out all of the X bars with each sample. So here, how many X bars can we get? We find that some numbers of X bar repeat, right? 0, 0.5, 1, 1.5, 2, 2.5, and 3, right? So what is the probability of X bar? What is the probability for each number of X bar? We can find that totally we have 16 possible samples, but in all of these 16 possible samples, there will be only one number of 0 of X bar, right? So the probability for 0 of X bar should be 1 divided by 16. Okay, so what is the probability for 0.5? We can find that 1, 2, there are two numbers of 0.5. So the probability for this number 0.5 should be 2 divided by 16. Okay, so here we can list all the number of X bar with its corresponding probability. So we can find that 0 X bar can be 0 and its probability should be 1 over 16. X bar can be 2 and its probability should be 3 over 16. Okay, so here this is the probability for each number of X bar, for each possible number, each possible value of X bar. So this is the probability distribution of X bar. Actually, this is the sampling distribution of X bar. This is what we called sampling distribution of X bar. Next one, we can use the histogram to represent the distribution. Here in the x-axis, we list all the possible value of X bar in the x-axis, and the y-axis means the probability. So we have already know that when X bar equals to 0, its probability should be 1 over 16. When X bar equals to 0.5, its probability should be 2 over 16. And we list all the probability. We draw the bars for each possible value of X bar, and we can get this picture. This is histogram. We call it histogram. So from the histogram, we can find the sampling distribution of X bar. So what is the property of the sampling distribution of X bar? Can you find that? Is there anything special? Can you find something special in the histogram of sampling distribution? Okay, so maybe most of you find that this distribution, this histogram, is symmetric, right? It's symmetric about 1.5, right? It's just like a mountain. So this is the peak of the mountain, and this mountain is symmetric about the peak when X bar equals to 1.5. So 1.5. What's the meaning of this number? Is that special? Let's go back to this slide. Let's think about it. We have four numbers in the population: 0, 1, 2, and 3. So if we figure out the mean of these four numbers, actually that is the mean of the population, right? So what is the number? So what is the value of the mean? 0 plus 1 plus 2 plus 3 over 4. So what's that? 1.5, right? Yes. So here we will find that the distribution of x bar is symmetric. Besides, it's symmetric about mu, about the population mean. So that's very interesting, right? Okay. So here, this is the next point we need to learn. So this is the property for the distribution of x bar. So in mathematics, there is a central limit theorem. So it means this theorem gives us some very important results concerning the sampling distribution of sample means. If all possible random samples of size n are taken from any population with mean mu and variance sigma square, the sampling distribution of sample means is approximately distributed as a normal distribution with mu and sigma square over n. So here we have already know the distribution of x bar is symmetric about the population mean, namely mu. So how about the variance? So here we already know that the variance of the original data is sigma square, right? We have already learned what's the meaning of sigma square, what's the meaning of variance, how to calculate sigma square with the data of our population. We have already know that. So here, when we draw samples from the population, we can get a new data which is consisted with the x bars. And we also know that the distribution of x bars is symmetric about the population mean mu. So how about the variance of x bar? The variance of x bar is still sigma square? Is that right? No. The variance of x bar is not exactly equal to sigma square. So most oftenly we use this symbol to represent the variance of x bar, sigma square x bar in the right corner. We can hear this is x bar, so that means this is the square. This is the sigma square of x bar. Actually, is the variance of x bar, because we said that variance is sigma square. So here, this one, variance of x bar equals to sigma square divided by the sample size n. So this is the formula for variance of x bar. So this is what we can get from the central limit theorem. it's very difficult to prove that. So you just need to remember this formula. This is the formula for variance of X bar. And here we all know that in chapter 2 we have another value which is called standard deviation equals to square root of variance. The variance is sigma square, so that means standard deviation is sigma. So here, what is the standard deviation of X bar? We can use sigma X bar to represent the standard deviation of X bar, and this symbol has another name. We can call it the standard error of the mean. So most often we call it standard error. So sigma X bar is different from sigma. Sigma is standard deviation. Sigma X bar is standard error. So from the later formula we can know that standard error equals to sigma over square root n.